All right, so today we're going to continue with this lab on arrays. And I also want to mention that I just updated this. I added this link here for quiz 3. So that's something that you need to start thinking about getting ready for that. And the lab that we're doing now is to solve problems that may appear on the quiz, or problems similar to the problems in the lab assignment will appear on the quiz. You could see those problems here. And these are problems that I have taken from last quarter's quiz. Actually, this is last quarter's quiz. So there's that assignment here, assignment 3, algorithms 2, which also looks a lot like the problems we're doing today, and will look a lot like quiz 3. All right, so let's move forward here. I'll see, last time we looked at this function, myMaximum, and we implemented that. That function takes an array A of integers, and arrays don't have any built-in mechanism of keeping track of their own sizes, so we have to pass around the size of the array as a separate piece of information. That's different than this function here, append, which we also implemented. In this case, the sequence of integers that we're passing in is represented or stored as an instance of the vector class. And the vectors have a built-in mechanism to keep track of their own sizes, as well as providing other operations that are useful when you're working with sequences of values. This n is not the size of the vector. This n is related to what the function is supposed to do. And here is just a number of additional problems to work on. And I thought what we could do is just go through these, unless somebody has another idea about how to progress here. I was just going to go through look at each of these lab exercises one after another. Is that okay?
Yeah.
All right. So we are in lab 6. And let's copy EX2 to EX3. And we'll edit EX3. And let's see, append vector. Here's the function signature. So we need to implement this function and write test code for it, I think. We need to write test code for that, although I don't think I state it there. So here's the function signature. It's the name of the function is append vector. So we have an input vector v and a second vector w. And the problem is to take all the values in w and append it, add it to the back of v. And so here's an example of what would happen there. If v were to be 425, and w were to be 11 and 3, then the result is 425, 11, 3. All right, let's take a look at that. That's a test case, and we'll try that test case specifically. Let's do that. Let's do this test case specifically. So v is 4, 2, and 5. 4, 2, and 5. And now W W is different. So I'll have V1 and W1. W is 11 and 3. And the size of W should be 2. Well, I'm not going to check that. So on the last pushback operation, a W1 will equal 11 and 3. And then at that point, we can call a function. So V1 is the first argument. That's the vector that will change. And W1 is the second vector, the vector we read from, and then append onto V. So when this is done, V1 should equal 4, 2, 5, 11, and 3. So we'll do an assertion for that. So 4, 2, 5, 11, and 3. We're checking to see that our function performed the test, that it passes the test, and performed the operation correctly. So I'll use this technique where we declare the function first, called a forward declaration, but we don't provide its implementation yet. We'll do the implementation after main. So it's not a requirement, it's just that that's the way I'm doing it. So this function returns nothing. So that's, if it's just an empty function, implementation is a good stub. Yeah.
Could you like implement it at the top though?
Yeah, we can.
You could declare and implement at the top if
you want. Yeah. I'll just do it that way. So now this cuts down on the number of lines of code, so which is nice. Just that every quarter I usually do it like this, and I forget to mention that you can use forward declarations to have a different organization to your code. But I would normally do it like this for small problems like this. All right, so this test should fail. This is test first approach. We're going to write our test, watch it fail, and then we implement the required functionality and then see the test succeed. And the problem with that approach is that the test code might have mistakes in it. But it's something you need to think about. There it is. So this assertion right here, that makes sense, right? Because we didn't modify V1. So these tests should pass. It's just position 3. We didn't modify the first 3 slots of V1. We just appended new slots 3 and 4. All right, so let's do this. You know, this is where you need to think about this. How are you? It's like a little algorithm, right? So how are you going to do this? There's a function called pushback. And what we need to do is, push the elements onto V. If we push 11 and 3, what do you think about that? They're going to pass the test. You just show that to your boss and say, well, time to go home. I'm taking a break, right? And then later when they find out you cheated on the chat and then you're in trouble. Okay. So this is a bad test. This is a bad implementation. And we designed the code to run correctly for the specific test. All right, that's a bad idea. And we could add additional tests that would catch that problem. But all right, so but anyway, we got to do, how are we going to do this? How do we append all the elements of W onto V? Anybody have a suggestion? Use a what? See, to me, I have a sentence in my head, and I just want to say it, but I want to see if any of you would say the same sentence. To accomplish this task, we should use a what? A for loop. Exactly what I would have said. Because we need to repeat something. We need to repeat the pushback operation. We don't know how big W is. I mean, we do for our specific test code. But W could have 1 million items. Now we got to do a 1 million pushbacks. In this case, it has 2 items. So we're going to do 2. So it's a variable number of operations. But it's an operation that has to be repeated. So naturally, you're going to use a loop. Well, what about the condition? What's the condition going to be there? What do I fill in for the question mark? Someone give me an answer.
5.
Huh?
5.
5? 5. So we're going to append. We're going to I will range from 0 to 4. If I ranges from 0 to 4, I'm sorry, that's V. I'm sorry, that's not right. It should be W. We're going to take out a W. So what happens if we put a 5 there?
Oh, it counts 0, right?
Yeah, it counts 0. So it'll run the loop exactly 4 times. So I will become 0, then 1, then 2, then 3, then 4. All tests passed. It's a bad idea, though. I want it to fail, but it's not going to fail for me because it's unfortunately C++ doesn't do range checking. So, yeah. Anyway, question there?
Yeah, if W was more than 5, then it would fail.
No, W has only 2 elements in it,
I
though.
don't know if it was. If it had like 6 elements, then it wouldn't get them all, right?
Yeah.
So if it was B.
So this will fail, right? Because W has more than 1. That's correct. That'll fail. And you know, it's hard to test C++. You know, when you have things like this happen. But what we could do is try to let's do the following. Watch this. Let's try this. See if we can make that fail. So this succeeded with 5. But I just added some data to the program. It still passes. Why is it passing? Push back. So it goes through here. Oh, because it goes off. It just doesn't. It doesn't it doesn't go past the end of memory. So this is not going to do anything. This one here is not going to do anything. Sorry. So it's hard to actually force this to fail. Maybe if I did this, I should get a memory exception. And that'll do it. Ah, what the heck? One more 5. It's just shooting. I don't get it. How is this? Are we even calling that function? Yeah. What is going on there? So we push back. I don't know what's going on. So W of, it's doing this. Watch this. So C out W of 5, 5, 5, 5, 4. That's the last item in that array. There's a 0 there. One more 5. You know, there we go. Finally got it to segfault. It's a memory error. So we're addressing memory that's outside of the legal range of memory that the process is allowed to access. So anyway, it's the, you know, what is, it's not 5, and although I can't show that it's not correct, it's, anybody else wanna go for this?
Like less than W?
Huh?
Less than W?
Less than W.
I was going to say V.
Well, but W is a vector, I is an integer, so we can't compare integers and vectors, right? Huh? There's two data types. W is a vector, I is an integer. So that won't even compile. We're trying to compare an int to a constant vector. See, it's showing it right here. How are you going to, what does it mean for a number like 0 to be less than a vector? What does that mean? That, you know, that 0 is less than a vector with 2 elements in it. That doesn't mean anything. How many items from W do we need to append? 2 in this specific case, but what if W were to have 100 items? Then we would need to append 100 things. Yeah.
You would need to for W, the vector size, right? Not
Yeah, the size. Yeah,
not
so
an actual number, but
exactly. How do we get the size of W?
V size.
Huh?
W size.
Yeah. W
Dot size.
dot size. You got to know this for the test, okay? So
That
start.
gives you like the integer of the size.
This expression, W by itself evaluates to a vector. This expression evaluates to an integer. Now we're comparing on the right-hand side of that equality an integer with the left-hand side, another integer. So that it'll take that. Yeah.
Would it be W or W1 dot size?
Well, W dot size is the number of elements in W. This is a very good question. W1 dot size is trying to, you've got to think about what happens with this expression. There's 2 steps of evaluation. Before invoking the size function, we have to resolve what W of 1 is. Well, W of 1 evaluates to an integer. And integers are not objects, and you can't call functions against them. So this would be a compilation error. Let's see. So it's hard to read this. a constant int, so otherwise known as, look at this. It says member reference base type constant valued type, and then it has otherwise known as constant int, is not a structure or union. So I'm not going to get into that, but that's, we need to call the function against the vector itself. That returns an integer that we can use. Let's see if that works. Well, I'll run that again. All tests pass, and that's correct. Any questions about this? So vectors have functions that you can call. Arrays do not. You cannot. If this was defined as an array, then v.size would be undefined. Arrays don't have functions. Arrays are inconvenient. They're part of the earlier version of the language called C. The later version of the language, well, it's a new language. The evolved form of C, C++, does provide an easier way to work with sequences of values called vector. What is the meaning of what is the meaning of this ampersand? Will this compile? No. Why will this not compile? I'm not talking about running, right? There's two things. We're going to compile, that generates a.out, and then we run it. But we won't even generate the a.out. Why? Why does the compiler refuse to generate a.out? I don't know about refuse. It's not that it's refusing. It's probably, it can't do it. Let's see what it says. Oh, it does do it. I'm sorry, Will, I'm wrong there. It does compile. Will it run correctly? It will not run correctly. Unless 11 and 3 happen to be in memory by accident where we want it to be. And that happened just last time. But it's not going to happen this time. Yeah, I failed on the first one. That's because we're working on a copy of the first argument. So the program, this append vector to function, depends on v1. The v1 we're passing in needs to get modified so that it's, it has 2 additional elements added to it as a result of calling the function. But if the function operates on a copy of v1, then when the function returns, the original vector will not have changed. All right, here it is. The next challenge. Who's going to get this? What happens if we take that out? Use like a job question. You could go into a job interview, and the interviewer might actually ask you these questions. If you think you want to get a job as a programmer in the future, you have to prepare yourself to answer these kinds of questions. What will happen? Well, first of all, there's 2 questions that I would ask. First, will it compile? And then if it does compile, will it run correctly? All right, let's start with the first question. Will this compile? Well, it compiles when we take this one out, right? So I think it'll compile. Let me make sure I save it. So it will compile. Will it run correctly? Will the test pass?
No.
How many people think it'll pass? I'm the only one. Here, what are we doing here? We're making a copy of W. That means the program can't modify. It's going to work with a copy of W. Is that a problem? Is it a problem that we're working with a copy of W? What's the big deal, right?
It'll be discarded after.
Yeah, it'll just be, we unnecessarily make a copy, which is wasteful.
But it was still added to it.
Yeah, it's just adding from a copy,
The copy.
an identical copy. Well, is there anything other than an identical copy? Huh?
So it'll still pass because it's still changing V.
Exactly,
Copies.
exactly. But, you know, we've been wrong before. So this is all a hypothesis at this point, right? But now we've got to make bets. Does anyone want to bet on the other side? I'll go 10 to 1 on $1. Okay. Maybe I should make that 100 to 1. Does anyone want to do 100 to 1? I'm getting nervous now. 1,000 to 1 on $1. Would I make that bet right now? I mean, that'd be an easy bet for you, right? But you might end up all giving me dollars. Well, the gambling is illegal, so the pressure is off. But let's suppose I was really risky, and I made a 1,000 to 1 bet on this. You all put up $1, so that means I could earn about $30 right now, or lose $30,000. Let's see. I just made $30. Yeah, but as we reasoned, that's wasteful. So why make a copy? Because maybe we're part of a larger program, like a video game, or something that is, you know, where performance is important. So we don't want to make unnecessary copies of data when we're running. So let's use a reference. Does that make sense? Okay. All right, let's copy EX3 to EX4. And I think it's going to be the same thing. That's another. Vector insertion. Suppose a vector V contains a sequence of integers ordered from lowest to highest. And so it's an ordered vector, right? So the small ones, here's an example. 3, 6, 7, and 12. You know, I'm not going to read anymore. I'm just going to go ahead and make my test case. 3, 6, 7, was it 12? I wasn't even paying attention. Let's see if I got that. 3, 6, 7, and 12, yeah. There's only one vector. Write a function called insert. So we're going to write a function called insert. So here we create our vector, v1. And we're going to write a function insert that takes this vector v as a first argument and an integer k as the second argument. So vector v is the first argument and an integer k is the second argument. The function inserts k into the vector so that it preserves the order of elements. For example, if v were 3, 6, 7, and 12, and k were 8, then after calling the function, v would be this. You can use the insert function to do the problem, but I'm saying don't use it. Okay, so there is such a thing as an insert function in the vector class, but we're going to reinvent the wheel. So we're going to provide our own implementation of this insert function. So the test will look like this. We call insert with v1 and 8. And then we need to test that, that v of 0 equals 3. And 1, 2, 3, 4. V of 1, V of 2, V of 3, V of 4. V of 1 is 6. V of 2 is 7. And V of 3 is 8. And V of 4 will be 12. Does that look right? That's a test, right? So let's run our test. This should fail. Use of undeclared identifier V. Go to V of 1. Okay. There it is. So as expected, it fails when we check for 8 because it didn't do anything. All right, let's do it now. This is the hard part right here, is it? Is this the hard part? This is where you have to be creative, I think. So take a mental note right now. How would you tackle this problem? You don't have to tell me. Just think, what are you going to do? Well, there's kind of a standard trick. And that's to append the number. And that's pushback, by the way. Let's start by appending the number. So we got it in there, and the vector is now one size larger, one element larger. But it's in the wrong place. So what we want to do is swap it with its predecessor until it's, let's swap it with its predecessor until its predecessor is smaller than it, or it's in the first slot. You get that? We're going to swap with the predecessor. So predecessor. How do you spell predecessor? Like that? Predecessor. How do you spell predecessor? Who knows how to spell predecessor? Are you all as bad as I am? No good spellers?
E-C-E-S-S-O.
Yeah.
P-R-E-D.
E-C-E-S-S-O.
Yeah.
Oh, good, thanks. Until larger. Maybe that's hard to understand. Well, let's do it like this. So we have a loop, and I'm going to use a while loop. Because, you know, a for loop is good when you know exactly how many times to do it. Actually, the for loop might even work better, now that I think about it. I'm going to use a for loop. And we don't know when to stop, right? You could do it with either loops. You know what? I should probably do it with a while loop. But we don't want to start at 0. We want to start at v.size minus 1. and I has to be bigger than or equal to 0. Or we could start here. That's the slot just before V. Do we want I to, I'm sorry, K. Do we want, if we start here, then I is the position where K is. And if we start here, I is in the position in front of K. So what is easier to think about? Here, I represents the predecessor. Here, I represents K. Yeah.
Right now, K is being put into the very back spot, right?
Yeah, so its position is v dot size minus 1. That is the position of K.
It's not just the full size, because if it's 5.
No, because remember, the index starts at 0.
Oh, that's right.
So look at this. Here, v dot size, before we do the append, v dot size is 4.
That 12's at 3.
And then when we do an append, a pushback here, that becomes, the size becomes 5. But the last valid index, which is where K is at 4. That's why we need to subtract 1. So here, I is where K is. So we could do it like this. We could, instead of that, we could say the position of K. We could do it like that. Position of K, just so that we can read it more easily. But you know, now I realize that the loop is too hard to read like that. I'm going to do it differently. So this is the position of K. The position of K will be v dot size minus 1. And then we'll have a while loop while the position of K is bigger than 0. Swap K with its, there's no apostrophe, with its predecessor until K is larger. Still, I don't like the comment, and that's, I don't want to write it all out, but that's essentially what we're doing there. So let's get rid of this. This is too confusing to use a for loop. So every time we do a swap, we need to increment the, we want to swap K. Well, let's see. Let's do the swap. We can do the swap like this. V of position of K gets V of the predecessor, position of K minus 1. That's the predecessor position, position of K minus 1. And then we need to decrement position of K. If K is bigger than its predecessor, then swap K with its predecessor. Otherwise, K is in its final position. So this is the swapping function. So we need a test there. If K is larger than V of position of K minus 1, that's the position of the predecessor, then we do this. And we continue the loop. Otherwise we're done. Does that make sense? But it's hard to read, isn't it? So let's make some changes. I'm going to declare position of predecessor, and I'm going to practice that word, predecessor. I think I got it now, but I'll forget it in a day. That's position of K minus 1. So this is the position of the predecessor. But you know, we could make this even more compact. This is now called refactoring. Of course, we don't know. Maybe we should check to see if the logic is correct. So we go into this. We push back the element onto the vector, and we compute the position of the value in the vector. And we call it position of K. It's just the size of V minus 1. And then, while the position of K is at least 1, then we want to compare K with its predecessor. If the position of K were 0, K would have no predecessor and would be in the right slot. So let's, just to make a mental note, rather than using position of K minus 1 in our calculations, let's compute in advance the position of K is the position of the predecessor, which is position of K minus 1, and then store it in a variable by that name so that we can read the code more easily. And if K is bigger than V of the position of the predecessor, if it's bigger than the predecessor, well, we can do it like this. We could make it even more simple, I guess. We can go predecessor. It's V of position of the predecessor. Is this making it easier to read or harder to read? Is that easier to read or harder to read? And we could get rid of this as well. And maybe this is kind of unnecessary. We just do this. Maybe this is easier to read here. We don't need position of predecessor anymore. We'll just get the predecessor. See, what am I doing right now? It's called refactoring. I'm looking at code which I believe, and I haven't tested it yet, I believe is correct. But I'm reorganizing it, renaming things, moving things around to make it more readable. So to make it easier to reason about the code, to understand it. And I suppose that's a matter of, it's a subjective experience to a certain extent, to a large extent. What version of the code is more readable than another version? It depends, obviously, on the people reading the code. It doesn't make a difference to the compiler, by the way, although the compiler would generate slightly different versions of the program, but they may give the same results. Are we ready to test this? We push k back onto v. We compute the position of k, which is v dot size minus 1. And while k has a predecessor, see I'm going to translate that into words. While k has a predecessor, while k has a predecessor, that means while position of k is greater than 0. See, this is the English concept behind this comparison here, this conditional. So when you read this, you translate that into, conceptually make its equivalent to this English language statement. So while k has a predecessor, while position of k is greater than 0, if k is bigger than its predecessor, then swap k with its predecessor, otherwise k is in its final position. Is that easier to read? Otherwise, we're done. So the predecessor is v of position of k minus 1. And if k is bigger than that predecessor, then we want to move the predecessor into the slot where k currently is. And then, oh, we're missing something. What about k? So after we advance this, we need to move k. Because the predecessor, now there's 2 copies of the predecessor. We do that. It's a little wasteful because we don't really need this here. We could put it here. So we never really look at v of position of k in the algorithm. We just, until we know we found the slot for k, then we can write k into that slot. So that saves a little bit of effort if we do it at the end. Now, if you were trying to optimize, maybe you would do it like that. But if you're trying to sort of be more, if you're concerned more about readability and this makes more sense to you, then do it like this. In the old days, it was important to shave off unnecessary calculations. But over the years, there's been sort of an increasing need for code to be readable rather than efficient. Now, of course, there are many situations where efficient code is necessary and important. But if the code is not readable, the system's never going to get built, and you won't have anything to work with anyway. And it's very expensive to build complex software systems, very expensive. Readability of the code is is critical. Let's see if that works. Assertion. So A is not in the right slot. What happened? I wasn't expecting that, so this is a real debugging session. What's wrong? Let's check the test code. All right, we push back 3, 6, 7, and 12. And then we insert 8. And the result should be 0 should have 3, 6, 7, and then 8 should be there, and then there should be 12. I think the test code is okay. And V1 is being passed in here as a reference, so we're modifying V. And are we passing in K correctly? K is 8, right? It's right there. Does anybody want to figure this out? I'm not looking at it now. I'm not going to think about it. Can you get this? See what the bug is? Why is the test failing?
What if it's supposed to be if K is less than the predecessor, you move it?
Ah.
That's what I was thinking.
Is that it?
I think so.
If K is bigger than the predecessor, we don't want to swap it, right? I just changed that to smaller. Does that make sense? Anybody ready to bet? I wouldn't go 1,000 to 1. I'll go 100 to 1 on this one. That worked. You got it. Good job. Good job on that. That's it. So that's those are 2 problems. Just before we break here, there are these exercises. I want to just briefly look at the schedule. What's coming up here? We need this on March 2nd. When is March 2nd?
Sunday.
That's this Monday?
Sunday.
That's Sunday? So this is due this Sunday. And then we're going to do this binary search lab is then due on next Wednesday, a week from today. And then the quiz will be in the week following that. So you have until Sunday night to finish up with this assignment and also get this lab finished. And then we're going to move on to this binary search lab, and that will be covered in quiz 3, by the way. Binary search is a single algorithm that we're going to look at. You need to implement this function using what's called binary search, and then there's this thing in here, an activity to understand the running time. And then there's going to be quiz 3. And if you look in there, on quiz 3, it's 100% guaranteed to have a binary search problem on the quiz. You have to know, you have to memorize that algorithm. So we'll be looking at that next week. All right. Any questions? All right. That's